past several years, CubeSats have become widely popular within the aerospace industry, and more notably within universities across the globe, as more teams utilize this platform to conduct scientific research, demonstrate new technology, and educate the next generation of engineers. So, CubeSats, for those of you who aren't familiar, are small spacecraft which can range from the size of a tissue box to the size of a shoebox, and they've become particularly popular because they are so much lower in cost and risk as compared to larger spacecraft. And it's because of this structure that CubeSats are allowing students to learn about the challenges that go into designing spacecraft firsthand and become much more prepared to enter their career in the aerospace industry. Yet, despite what CubeSat projects can offer students, some aspects of the student experience can be very different from what is done at the industry level, simply because, even though both are designing spacecraft, ultimately these are two very different architectures, both in technical and programmatic terms. So, given this, how exactly might student-led CubeSat projects differ in the areas of management, development, and testing from larger spacecraft that are developed at the industry level? Now, if this question intrigues you, then stay tuned for what we will explore in today's episode of The Art of Space Engineering. For any new listeners out there, I am your host, Sarah Rogers, and today I sat down with Professor Chuck Boehmer to chat about this topic in a little bit more detail. Professor Boehmer currently teaches systems design at ASU, but in the past he's served as a test pilot in the Navy and has systems engineering and program management experience from Lockheed Martin and General Dynamics. So, with this interview, I had a bunch of questions about how larger spacecraft are designed, developed, and tested, and then throughout the conversation, I shared my counter or similar experience from working on the Phoenix CubeSat during my undergrad at ASU. We also dove a little bit more into his background in systems engineering and project management. So if you're interested in systems engineering, I hope you find some useful resources from this interview. So with that, sit back, relax, and let's dive right into the interview. So welcome back. Thank you again for donating some of your time to talk with me today as we kind of compare and contrast some experiences on working on both small and large spacecraft alike. So I have a bunch of questions on design and testing, but I thought we would start out with exploring your experience a little bit more first. So I know that during your time at Lockheed, you worked on spacecraft for the intelligence agency, and I take it that you're probably not allowed to talk about what the payloads for those specific missions were. Am I correct? True. So like I can't ask you if you worked on like space lasers and if that's really a thing or...
No.
Okay. Okay, I didn't think so. Okay, interesting. So not space lasers, but probably space lasers. Got it. So I guess going away from that topic, I guess we'll say, so your experience at Lockheed, you said last time, was more on the program management side. So I thought it'd be cool to talk about what some of your responsibilities were as a PM and what made that experience rewarding for you.
Okay. Well, basically as a program manager, as NASA calls them, project managers, they're one and the same. But you're responsible for the entire program, the system performance, the schedule, and the cost. And most of the design and performance issues up to a point are the responsibility of systems engineering. It's extremely, especially if you have a schedule issue, it can be extremely stressful, but I think one single thing that made it most rewarding is working with all the people. And I think that's, it sounds cliche, but it really isn't. It's the people that make the program. Mm-hmm. And being able to work with all of the people in all the departments and constantly learn lots about every single thing about these programs, the control systems, the electric systems, propulsion systems. You just increase your knowledge with every time you get involved with it, and it's really interesting. For me, it was. but the big rewarding experience was all the people and working with them.
So in addition, were you mostly like just the primary interface between like stakeholders and then the rest of the team, more so
Yes.
than like systems engineering? Okay.
Well, the part of the responsibilities, or one of the big responsibilities of systems engineering, is that they really are the interface between the contractor program and the customer program. And early on in the program, hopefully the two program managers, the contractor and the customer, stay out of the way and just watch and get a big foot when you need it. But it's the systems engineering team from the customer and the systems engineering team from the program manager that really do all of the initial interfacing. And the engineers, the hardware engineers, software engineers will do some interfacing, but it's mostly the two systems engineering organizations that are really responsible for getting the program going up through the PDR. And after that, the design engineers really have a lot of say in the program, and a lot up to that point too, because you're starting to get well into design. But it's systems engineering job to get you there, and to get you from PDR to CDR.
Right. So you mentioned before as well that I know you have systems engineering experience in the Navy. So which one of those did you like doing more? Being a systems engineer or being on the program management side?
Well, probably on a little of both, because you're responsible as a program manager for systems engineering, and the chief system engineer works for you. So
Right.
so you really can get involved, but not as much as you'd like to as a program manager. You need to stay hands off and let everybody do their own thing. So when I was in the Navy, it was a little more hands-on as a system engineer in some of the programs that I worked, and that was really a lot of fun. I was a lot younger then, but it really was very enjoyable. But so was being a program manager. Just more headaches is all.
Right. Yeah, I as serving as the PM for Phoenix, I can definitely agree with a lot of that.
Yeah.
And I guess like the benefit of being on more of a small team, like we were mostly just like a small team of people kind of trying to figure things out at the end of the day. But yeah, it definitely allowed me to be a little bit more hands-on as the PM and kind of take a PM / systems engineering role, because none of us knew what we were doing and we were all kind of just trying to figure it out.
Yeah.
So
And it doesn't change all that much with a large program either. It's just a matter of scale. You still have the same thing. You've got to have some kind of a manager, whether you call them a program manager, program leader, or whatever. You still have some form of systems engineering, or at least going through the process. You have integration and test, verification, validation, and so on. And it's only a matter of scale is the difference. And sometimes the pressures are a lot different too. The customer can make a huge difference, and also the rationale for the program. And a lot of the programs that I worked on were a matter of national priority, and so there was always pressure to try and maintain schedule and maintain launch. Whereas with some other payloads, you don't have quite those pressures, but you do to a certain extent, because if you miss schedule, it costs more money. It always costs more money. And a friend of mine that in the Air Force that I used to work with a lot used to say, the optimum amount of money for a program was the day you signed the contract. And after that, it always went up. It never failed. And if you tried to compress the schedule, it costs more money because you're putting more time in. And if you move the schedule out, it costs more money. So staying on schedule and on cost is the only way to get there. But it rarely happens, unfortunately.
Yeah. I guess our experience is a little bit different because we got, so we were funded by NASA, but we got all of our funding up front. And we put all of that towards the hardware and any additional supplies we needed, because we didn't have a lab, and we didn't have enough ESD mats, and we needed to buy proper equipment so we could make a flat set and make sure that everything was being handled very safely in terms of ESD control. And so yeah, for the most part, it was kind of like NASA was very hands off, and it was mostly just us kind of pushing our own schedule until eventually we were manifested on a launch. And once we were manifested on a launch, that's when schedule became very, very real.
Yeah.
And we had to figure out exactly, like, at a minimum, what we really, really needed, so we could make sure that we had a robust system that would go to space and do exactly what it needed to. So yeah, but even that date was defined by us too. They said, when can you be ready? We told them a date. The first time we did not make that date. The second time we did. But yeah, so it was and pushing back cost time and work on their end when we did do that. But so that we really didn't want to do that, but we definitely weren't ready to launch the first time that we said we were. So yeah, so that's I guess that's the experience that we didn't quite see in working on our CubeSat. So that's interesting to see that side of things, and how larger and smaller programs might be slightly different. But then again, that's also just our experience. I don't know how many other, I know like other CubeSat teams can work with like other NASA centers on collaborating on different payloads or other things. So that's just our experience. But coming back to systems engineering a little bit, for any students who are listening to this podcast, I was wondering if you might have any advice for any students who are interested in pursuing systems engineering as a career, in terms of like what good focus areas are there to really study and learn. It seems having a really good basis in electrical engineering can definitely be very helpful, because electrical engineering and even like software, just from working on Phoenix, software is basically your entire satellite.
Yeah.
So understanding those is really critical to just knowing what questions to ask.
Yeah, double E in software, or they kind of run the gamut in any kind of satellite. And but I think if someone is really interested in going into systems engineering, I think the first thing you understand is it's rare that larger companies anyway put brand new employees into systems engineering. Employees brand new meaning they don't have any experience. They're fresh out of a university. I think the best thing that can be done is to, if they're really interested, is to try and find an online course, or at least at ASU, if they have a technical elective they can take. CC does have that SES 405 systems engineering course, but also there's a lot of online courses available around the country in systems engineering that if they didn't have the time, they could take those. Or the Microcosm, the publishers of the SMAD book.
Oh yeah, SMAD is great.
They have an excellent systems engineering book. It's actually bigger than the SMAD book that you have.
Oh, so it's not NASA Systems Engineering Handbook. It's something completely different.
No.
What? I didn't know this was a thing.
Pardon?
Googling this right. I didn't know this was a thing. Googling this right now.
Can you see this? Let's see. Oh.
No, the green screen's like covering it.
Here.
Applied space. Wait.
It's Applied Space Systems Engineering. Okay. And it's the same guy. It's Wiley Larson, and it's done by Microcosm. And it runs, I think I got it for $70.
All right, I will look at this.
It's well worth having. It's really well done.
Yeah, because I've read through the NASA Systems Engineering Handbook, and that's pretty good, good at outlining the general,
Yeah,
organizational process of how things come together.
yeah, that's not actually bad. And the Defense Acquisition University has a good systems engineering handbook too.
Hmm.
DAU, if you look up Defense Acquisition University, uh, they've got a systems engineering handbook. I actually believe it's better than NASA's, but it's not bad. And NASA's is good too, especially if you're going to be working NASA programs that 7123 you have to abide by.
Hmm.
And so they're both of those are very good.
So what does
Uh,
the DAU book go into that's not really covered in the NASA
it's
SE
just the
handbook?
way it's done,
Oh, okay.
the
So it,
organization and
mhm,
what's said. I mean, it's all the same. You
mhm.
know, system SE process is the SE process, but it's just the way it's put. It's very very well done.
Hmm. Okay.
Uh, and so's NASA. It just I think is just a matter of individual preference.
Okay.
Um, but this applied space systems engineering is really good, and I think the best thing is it looks at everything from a space system standpoint, and it's
Mhm.
got two very very good examples as it goes through the book. One is FireSat, of course,
Yeah.
and I forget what the other is. It's more of a software type program,
Okay.
uh, but they do a good job of using those as examples as they walk through the process.
Cool. Wow, thank you. I will check that out. That's that's awesome.
So, and I think that without taking any course and just looking at either one of those handbooks, a student could get an excellent understanding of the system engineering process that they may not otherwise get. I think that anybody that wants to go into systems engineering needs to be able to see the big picture, and also be able to, and that means being able to see the forest for all the trees. You
Hmm.
can't get stuck on a single tree. Um, Something else I just happened to think of is that they could at least see whether they maybe had the personality for it by looking at those Gentry Lee videos.
Oh yeah.
One, so you want to be a system engineer,
Yeah, that's a
and the
great.
other one is a canvas is blank.
Hmm.
Both of them by Gentry Lee at JPL. Um, those are just, I think the so you want to be a systems engineer is an excellent video. And if you find a couple of traits in there that you're not comfortable with, then you're probably not going to be comfortable with being a systems engineer.
Yeah, that's fair.
And I think that one of the very first things he says, if I remember correctly, that I think is really important, and I've seen it now work out, is you have to be comfortable with change.
Yeah.
And if you're in electrical power systems or propulsion or any of the other subsystems as a hardware software engineer, change isn't that big a deal, but in systems engineering, up until you get to critical design review, everything is changing all the time.
Hmm.
And like he said, your job is never done. You go to bed and the next morning you might have to start all over again.
Hmm.
Yeah, and if you're not comfortable with that, it'll drive you nuts. So I think those are some things that they can look at as either the NASA 7123 Systems Engineering Handbook, the DAU Systems Engineering Handbook, uh, learn the systems engineering processes.
Yeah, and going off of resources, I think one of the reasons why I wanted to make this podcast as well is I think really like the one of the best ways that you can train yourself for becoming a systems engineer, or just see if you like it, is by reading technical papers on how things were designed and learn exactly what other people have done and the lessons that they've learned, and that kind of
Mm-hmm.
even because really you get better at systems engineering and knowing what to look out for as you get experience. And so the question is,
Yes.
well, how do I get myself, how mentally can I get myself like 5 years ahead so that way when I go into the workplace, like I know exactly what I'm doing
Yeah.
and I'm able to contribute in a way that's constructive, and I'm, you know, I'm helping catch issues because everyone's so busy, everyone's got like 5 million things on their plate, and just having as many minds on a problem as possible is really helpful. So.
Yeah, in reading papers on lessons learned, most every program, I know for NASA, also DoD, when after launch or after something goes wrong, there's always a lessons learned paper. And a lot of times that goes back into, a lot of them go back into systems engineering. If you look at Genesis, for example, and go look at that, lessons learned paper. If you go and that Tyro satellite at Lockheed, that fell off the bench.
Oh yeah.
The lessons learned on that one is incredible. I mean, it's just it's a comedy of errors, and you can learn lots from that. And that, I mean, as simple as how important documentation is. When you've got a satellite sitting on a bench, you have to document every movement, and it has to be truthful. That people actually signed off on things that they never looked at. There were 12 bolts missing off of a turnaround table, and somebody signed off that they were all there. And before that, somebody took the bolts and never documented the fact that they did. They needed it for the bolts for something else.
Oh, that's lovely.
Isn't that lovely? Yeah. And when they went to turn it over on its side, the bolts that were there couldn't hold that satellite, and off it went.
Documentation is, documentation. It's so important, and it's something that we really took for granted. It's something that university teams definitely shouldn't take for granted, because I mean, at least when we
boring,
started,
it's boring, and it's not very sexy, but it has to be done.
Well, and especially for university teams too, it's I mean, like when you've got homework and you're not working on the spacecraft full time, like adding an additional work to really document things is it's taxing on top of just trying to get the work done in the first place as quickly as possible. And so I mean, like one of the questions that we had when we first started was like how detailed do we really have to go with like keeping track of everything? Because we're not like a NASA system, but the reality is that it is still really important. You should do configuration management and track software versions and what things have been qual tested.
Absolutely.
And do demate logs and have people like actually sign it off and have an approval process for all of that. Because if you don't do that, that's just like the easiest way that you can become disorganized and miss something. So I think that level of documentation is one of the best things that university CubeSat projects can teach people, in my opinion.
Requirements management and configuration management. It can turn into a mess, and and you take, again, thinking about scale, just think about the requirements document for the James Webb Telescope, for example.
Oh my God.
And and how quickly that could get out of hand. If people just start doing their own thing. And I mean, there are just pages and pages and pages of those requirements, and they have to be managed by a configuration control board. Everybody's got to be singing from the same sheet of music.
All right. Well, okay. So segueing off of this introduction to like systems engineering and just developing spacecraft in general, CubeSats have provided like really great ways to test new technology and with very little risk. But in general, heritage really matters a lot with spacecraft design, especially larger and much more like scarily expensive spacecraft than CubeSats. So in the programs you worked on, was hardware usually just taken from heritage designs and then maybe modified slightly to meet whatever mission requirements you were working on, or did you have to develop any new technologies as well?
It was really all of the above. Most of the satellites that I was involved with were one-offs.
Okay.
In some cases, you might have built maybe two of them, and then the design change for the same system was so great that there really was no heritage you could use. Probably the biggest heritage between spacecraft in those days was the electrical power system. Pretty much the same systems were used over and over again. It was just a matter of placement and analysis of how much you need. But there was always pressure to use, heritage if you could, because obviously it was cheaper.
Right.
It got also in the early 90s, there was a huge change to take a look at commercial off-the-shelf systems and get away from space qual. That was particularly true on NASA programs and non-military programs. But the heritage was always a push.
Mm-hmm.
But when you were looking at the one-offs, building one of a kind or significantly changing the technology from one satellite to another, even though it was somewhat the same system, they were totally different. You figure a lot of those satellites back in the 80s and 90s, their design life was 5 to 10 years, but they were lasting for 20. And the technology went through 3 or 4 or 5 changes by that time.
Mm-hmm.
And a satellite that may have been called Program X, all the way through, the number 1 and number 3 looked nothing at all like each other.
Mm-hmm.
And, it was probably number 3 was more compact, better usage of solar cells and batteries. The comm systems changed constantly back then. They still are. That's about the time we were really getting into low power Ka, Ku for onboard comm systems. And so a lot of the antennas were much, much smaller than some of the old S-band systems that were on the older satellites. So things changed so much that, like I said, with the exception of electrical power, heritage really wasn't there. And even within electrical power, batteries changed to lithium ion batteries from the huge batteries of yore. What used to be thought of as high efficiency gallium arsenide solar cells at 18% are now up to around 35-40%. And
Oh, wow.
And so the heritage there, you didn't want to go out and use gallium arsenide when there was a lot more efficient cells available, even though you put them on pretty much the same way. The manufacturing and the engineering process to install them was pretty much the same. But you ended up with lot smaller arrays for the same amount of power required and fewer batteries for the same amount of storage that you wanted to have. And so you could change the looks and the structure of the entire satellite. So, but again, as satellites became more and more expensive, the push for heritage became greater and greater. Why can't you use what they used on another satellite system? Just build it again. You can do it, with your eyes closed, and then, make that work. And in some cases, NASA insisted on that, and in some cases, the Department of Defense insisted on that. Use the same electrical power system as you used on Program Y.
Mm-hmm.
And it forced out the design, and the design engineers didn't like it sometimes because it made the satellite bigger than they thought it had to be. But you could run into that problem all the time anyway.
Right.
You know, design people like architects or artists, want to have, room for their own imagination and not have somebody tell them what to do. So,
Right.
but there's always that push to use heritage systems or systems that were built. And it's one of the first things in the systems engineering process when you look at your requirements analysis. You want to look back at technology and see what's available that you can bring forward into your own system, and then make a decision via trade-off study as to whether that is using that, if the measure of effectiveness is the same as using a new system or more than or less than, and then conduct your proper trade study to determine what to do. Mm-hmm. Sometimes you're told what to do, and okay, the customer has the money, and they can tell you that.
Going off of that a little bit, so I mean, like one thing that I think is really cool, at least for like CubeSats at the university level, is that it really allows students to really learn those subsystems, because for a lot of teams, so like we got very lucky in the sense that we applied for this student flight research opportunity within NASA, and were funded like $200,000 in order to put the satellite together. But those opportunities are really hard to come by. And so, I mean, for universities that want to build a CubeSat, like they have to, design it from the ground up and really learn how all of those systems work. And so I think it's awesome that you get that experience from working on something like this. Mm-hmm. For a lower cost, you can still be flexible with the design and kind of put a system together. All of our hardware was basically heritage, and that's useful because you're essentially getting hardware that is very reliable and that's worked in space in the past. You don't have to worry about missing all of those complexities that you haven't, you wouldn't even know to think about, because you're learning about these systems for like the first time, basically. And that's especially important with more of like the protective measures, especially when it comes to like EPS systems, I felt. I think in terms of commercial off-the-shelf hardware, while it definitely made our job a lot less complex, since we didn't have to design any of the key components, we definitely became limited in some areas and had to make compromises based on what we could do with the project, just based on what was out there. But it seems like with larger spacecraft, you have a lot more control over essentially every part of the design. Whereas with CubeSats, you can have that if you're designing your own thing, but it's not as complex or robust, and you're taking a lot of risk in doing that. But if you buy commercial off-the-shelf hardware, you really don't have that level of control, which can be frustrating and lead to compromises.
Yeah.
But yeah, so that's interesting. Did you ever run into any issues like that using commercial off-the-shelf hardware, or even like heritage hardware, or is it mostly just in terms of I guess what people wanted to include and maybe what they didn't want to include?
No, I can't remember any issues like that we ever had. Yeah.
There's nothing wrong with that.
No.
That sounds like a good thing, so I'll take that.
It was a good thing.
All right. So one area I do want to cover in this podcast is systems integration, since it's really not something that you can really teach in a class. It's very difficult to like teach people where to place things within a satellite. So I was curious on, how did you decide where components should go, and was the layout generally very similar between the different programs that you worked on in terms of where hardware went, or kind of like what we were talking about earlier, it's since there's so many years between working on different programs, do things get smaller and less complex, and you have more flexibility in the system?
Yeah, I don't think there was at all a standard of where things went. I think they took a little of, what do you call, the concurrent engineering up front, between all of the hardware and software people it's like a puzzle. And, what is the best design for the structure in order to get everything that we need in there. And that's why the structure is really one of the last things that's designed. Everybody needs to understand, or the EPS people need to understand what the electrical power system requirements are and the propulsion all the way through. And then you have an idea of what your weight size and power are for every single subsystem, and then they can get together and they force the structure around it. And also thermal control plays a huge part in where things go.
Oh yeah.
Whether it's in LEO, MEO, or HEO, plays a big part of where things go. How much are you going to be facing the sun? How much are you going to be facing away from the sun? So thermal plays a huge part in where things go. And also you get to the point where you have to take a look at going through the Van Allen belt and hardening against radiation. Where do you want your computer components to go so you don't get so you're not taking high risks with single event upsets all the time, and the possibility of losing a computer. And so again, it's kind of like a puzzle, and you take a look at all of that and try and look at the best place for the best placement for everything, and then put it all together. And of course, all of that has to be done with the sensor in mind. Whatever science you have on board, or whatever sensor you have on board, that's the reason for being of everything else. And
Right.
So that has to obviously be taken into account. You have, are you doing imaging? Do you have a radar? Are you just an RF receiver? Are you a receiver transponder, as in a CubeSat? And all of that, you have to pretty much design your satellite and all of the subsystems around what the sensor requires. Again, that's the purpose that you're up there in the first place. So everything has to match that. And then finally, you've got to worry about mass, centers of gravity, moments of inertia, and things like that. And once you kind of take a trial and error and put it all together, you may have to move some things around because your moments of inertia or your center of gravity aren't in the right place for that particular satellite, and you need to move it one way or another, up, down, X, Y, Z, whatever it is. And so you shift a few things here, a few things there, and you finally, get to where everything needs to be. So it's really kind of trial and error in a sense, but it's also, you can take a look at it all from an engineering standpoint, and before you ever put it all together, you have a very, very good idea of what it's going to look like, from a mass moment of inertia standpoint, which is really important when you're, on the pad.
Right.
So it's a game, but it's very scientific.
Do you have any stories of any interesting challenges that you ran into when it came down to choosing where components went?
Probably the only story is that we had a satellite pretty well designed around a sensor, and the customer changed the sensor on us, and which required almost a complete redesign. In that case, we tried to keep everything we could as close as possible to the original, but because of size, weight, and power, we had to move a lot of things around. It was the same mission, but a different sensor altogether. And it caused a lot of heartburn with the design engineers. So
yeah,
and it was a matter of it was what is referred to as beneficial risk technology. There was a technology breakthrough somewhat overnight. It allowed us to put a much better sensor on board, but the size, weight, and power requirements of that sensor were totally different than the other one, and so it wreaked havoc, throughout the design world with that particular satellite, and a lot of things had to be moved. It was, I want to say, major redesign, but it really wasn't.
How far along were you at the time? Like, were you at CDR or and you'd started manufacturing things? Oh,
so
gosh.
we had to redo CDR, actually.
That's fun.
But
I'm so sorry.
yeah, that was a ball. But I think, overall, when everybody saw what this new sensor could do, I think most people were okay with it. And didn't mind the extra work. And it was just one of those things that worked out, and the long and short of it was the satellite was a huge success in terms of a total turnaround and redesign in a very short period of time, and it took the whole team pulling together to be able to do that.
How short of a time?
It really is a puzzle when you first start out as to where to put everything, and it's kind of, everything has its place and there's a reason for it.
How short of a time did you have to turn that around then?
About 6 months.
Oh.
And that's not very much.
Yeah, that's not.
When we're 6.5 years into the program. So the best thing that happened is that we forced out, what we did is made a pre-configured interface for the sensor design company, and told them that the sensor had to fit that pre-configured interface. And so as far as the external portion of the satellite was concerned, we really didn't have to worry about it. What we had to worry about was what the sensor did for increased power, what it did to the moments of inertia and the mass. And then we had to kind of make everything fit to that. But at least we forced it to fit on the satellite, so that for the external structure to fit the sensor on it, there was no change.
Oh, well, that's
we
that's
kept
great.
we kept the same interface.
Okay.
So, and we just called it a pre-configured interface, and that they had to match, and it was difficult. It put the onus on them, but turned out it wasn't that difficult.
Did you initially require it that way, so that way, you
No.
knew you only had to be concerned with like mass and power, or was it just based on how you were designing the structure, that's just what you guys decided to do? Or
that's what we decided to do. Yeah.
Did you continue?
We thought we were going to head for a total redesign, and then somebody came up with that idea, is that they could redesign the interface a lot faster than we could design the structure, redesign the structure. And it took a lot. It took a lot on their side, and a lot of thought, and a lot of really good engineering, but we were able to do the interface the same.
I had a question. I forgot what it was.
Oh, a senior moment.
I already have gray hairs.
Do you?
I do. I felt from working on Phoenix. I've found gray hairs.
Oh my goodness. Oh, Sarah.
I was very sad. There. I feel it. I'm gonna lose my hip next or something. I don't know.
Oh, that's great. Well, I'm sorry you have to put up with that. But that's what happens. Just think about your future now.
I know, I know. It's just going through undergrad and a CubeSat. That's all it took. Everything else is just going to accelerate the process. So I guess going off of the structure, for larger spacecraft, like how do you go about doing fit checks and making sure that the structure's been, I guess, designed properly with everything in mind? Is that all really mostly just done in CADs? I mean, like to check things, we made like 3D printed models to make sure that we could practice assembly procedures and that, actually putting it together, we didn't run into any issues that had to, required a redesign in CAD. Um, so did you make anything like that? Did you have to put it all and design it all in CAD and then just make engineering models and then
Pretty much, we
mhm.
got to the point where everything was designed on CAD and then put together and or manufactured. It used to be that engineering models were the big deal. You'd just build a satellite that you may or may not ever fly. But as time went on and satellites got so much more complex and so much more expensive, it just became out of the question to have that luxury.
Mhm.
And so the number one that was built was number one that was going to fly. Every once in a while, what you would do is build number one and it would fly number two. You'd find design changes or fixes that you wanted to make or needed to be made. And so then you'd build number two, fly it, and then reconfigure number one so that it was like number two.
I see.
That makes sense. But basically everything was done by CAD, and you just manufactured from that. And it was pretty good stuff. I mean, we had very, very few problems
Okay.
with that.
With Phoenix, I think, and especially I think this too, because it's such a small volume. I mean, for the most part, the 3D printing models that we made work really well, and so we
Mm-hmm.
moved, um, not like super quickly, but we didn't have to do like a massive redesign in order to feel confident that we could start fabricating. But definitely once we fabricated all of the brackets and then started, developing harnessing and trying to actually, really put things together with what we had machined, like we did make a lot of like small modifications to
Mm-hmm.
support better cable routing or, when it came time. So like we have an access port which has a USB interface so we can upload software and a DC charging port so we can charge it without having to power the solar panels.
Good.
Like when it came to time to fit those too, we found that those needed to be like a little bit wider to support, like putting the actual cable in there.
Mm-hmm.
So we definitely had to machine it and then make a couple of small adjustments in order to make sure that everything interfaced correctly. Did
Yeah,
you
well,
ever?
3D printing, I think, has really probably helped, in that region. And of course, that wasn't available until, just a few years ago. That's a relatively, recent technology, that's available. And boy, I would have loved to have had that,
Yeah.
back then. Um, but the CAD, there were a number of times where, just like what you said, when you were manufacturing, bits and pieces and machining them, you may have had to machine them a couple of 3 or 4 times to make it right,
Mm-hmm.
but it wasn't usually that big a deal. But the machine shops were certainly busier in those days than they probably are now, just because of 3D printing.
Mm-hmm. So since you really only had like one since it really would have been expensive to make two of the exact same spacecraft, was the first time that like the whole assembly process really came together, like during systems INT, and there wasn't, and so any fix that you found in that process, like basically had to be made kind of much later on.
Well,
Like,
we made a lot of fixes on the fly, but I think what we did then was I think we did a lot more subsystem testing than is done now. Again, it just it cost a lot of money.
right.
And it's still an argument as systems test versus subsystem test. But when we put a subsystem into the spacecraft, it had been thoroughly tested. And then when we went into system test, if something went wrong, there was generally very little doubt about what it was that was wrong. And so the fixes that had to be made were really minimal. I don't think I never saw any kind of what I would call major redesign or fix that had to happen because of something that went wrong in system test.
Okay.
Or thermal vac or shake and bake. Never, things went wrong, but they were typically minor that could be fixed. When you didn't have to tear the whole thing apart.
Okay.
And that was the result of really good subsystem testing, but that was also cost a lots of money to do that.
Okay, I guess one more. I'm not sure if we went over this. Maybe we've answered this question, but I'll ask it just in case. So designing a system layout can be pretty challenging, and you always tend to find stuff later that you don't always see or understand with CAD. So like one example that I'd read about is that with Spirit and Opportunity, they installed a battery on the bottom of the rover, so beneath the main electronics boards, because they thought it would place the center of mass a lot closer to the ground. So they're just using engineering. They're just thinking about it as an engineer and in terms of where to place a component. But this ended up being a very high risk operation. So granted, those rovers were pretty much like packed with everything, but anytime they had to remove the battery, a lot of risk was involved with just getting the main electronics board out so they could get to the battery itself. So, and that was something, that's one of those things that the engineers like laid awake at night, wondering how it went. And that was definitely something that they fixed with Curiosity. They ended up basically flipping the rover over. So everything was put into the rover basically when it was flipped upside down, and they made sure that there was enough room to where they could actually get to every single component that they needed to. So the question, going off of that, the question that I wanted to ask was more of like, have you ever run into any major challenges like that with systems integration late in the game, kind of when everything's already been designed and fabricated, and you're going through the AINT process? Granted, those rovers are a lot more compact, like I said, but yeah.
The only thing that I can think of was what we talked about already, that major design change with that satellite. There have been some really dumb integration problems. When you go to plug a subsystem into the wiring, you find out you have two male plugs. Things like that, which are simple fixes, but they're just, how did this happen? Somebody didn't follow the process somewhere along the line, and little dumb things like that are really the only thing that I've ever seen. I'm sure there were all sorts of examples, but I never ran into them.
Okay. That's good. That's a good thing.
Yes, that's a good
There's
thing.
nothing wrong with that at all. All right. All right. So we've spent a lot of time on systems design and systems integration, but the real fun part is testing,
Of
um,
course.
for sure. So going into
Software.
more of the development and testing side of things, one thing I was really interested in poking about was the flight software, since you know, really, like I was saying earlier, it's basically your entire spacecraft. If your flight
That's
software
right.
doesn't work, then you can't perform your mission at all. Um, so I'm curious to know like what the software development and testing process was like. Like would people just develop something and make it on a Linux target, make sure that it worked, and then go and test that on the actual hardware for the most part?
For what we always did was have simulators, spacecraft simulators that were part of the contract. And the software was tested and tested and retested and then retested before it ever got to the spacecraft. And then finally, when everybody was happy with all of the testing through the simulator, on the ground, you would, test the software, command by command. It's a long, involved process, as I'm sure you've seen, but that's how it was done. And then finally, again, once everybody was happy, and it went through its verification. When you had final verification of the flight software, you loaded it up, and then part of on orbit testing was one command at a time.
Mm-hmm.
You'd start off, and of course the first thing you got to do is get power to the spacecraft, especially if you had a long time to orbit. Your batteries were running low, so you had to put out your solar arrays, but you did that very, very slowly, command by command, to get those solar arrays out.
Don't do those tests take days to like
Oh,
fully unfurl the?
they can take months.
Oh.
But on orbit, of course, you're talking days. But in the plant, you're talking, flight software test are months long. And going through that and just making sure every little thing is right, and going over it and over it over it. And it's why, flight software, of course, is one of the last things, again, that comes into final design, because it has to incorporate every change that's been taken in, up through and including CDR, if there are any changes, and how does that change the command structure that goes to the spacecraft.
That's interesting. So like had um we had a very different experience on Phoenix. So we purchased commercial off-the-shelf hardware, but we didn't get eSIMs with it. So really the best way to actually develop all of the flight software was to just program everything on the actual hardware. And so it was like we had one OBC, and we would basically just develop different software applications, whatever we were working on, run it, make sure that it actually it built properly, and then we would have to load it onto the OBC, test it, make sure it worked. You would pretty much almost always get a seg fault, and then we'd have to go, oh, okay, so this is where the error occurred, fix that, test it on the OBC again. But even then you're testing like everything on hardware. And so there was one notable time where we accidentally erased the firmware, part of the firmware of our camera, because of that, because we didn't have an eSIM or anything. So we ended up having to ship it back to the vendor in order for them to fix, which, and it was they turned that around very quickly, and that was awesome. We were definitely very grateful for that. But yeah, that's definitely was a risk in terms of incorporating that. But it's also probably why it also probably allows the components to be cheaper as well, I would imagine. So
Yeah.
How many people usually work on the flight software for a large spacecraft?
Oh my God. Think I had one program, there was about 150 software
Oh my,
people.
wow, that makes a lot of sense.
Yeah,
But that's kind of crazy to think about when I'm for the most part, I'm used to CubeSats or instruments.
yeah. And of course, you know, again, it may be different today because of the software changes. We were back then, I shouldn't say back then, but everything was in Fortran.
Mhm.
And then there was this huge shift just before I left Lockheed, as a matter of fact, to go to C++, go
Okay.
from Fortran to C++. And of course, that was a major change, you know, to you know, change all that software. But
Mhm.
you know, Fortran was it was labor intensive. It's
Yeah, we
good
just
good software though.
yeah, we used C for pretty much everything
Yeah,
that we did. And I think the largest that our team really got was like 8 people for the
yeah.
most part. So very far from
But
150.
you're talking, you know, you're talking at that time, you know, thousands of lines of code.
Oh yeah.
You know, thousands of lines of code.
Yeah. And you know, even for a CubeSat, like there was still a lot of stuff that we had to take care of for Phoenix, but it definitely was nowhere near as complex as
Yeah,
incorporating everything that you guys need to with a large
yeah.
spacecraft, of course. Segueing into a different system, so even though you can't talk about your space lasers, I would imagine that pointing requirements are probably some of the most they're really some of the most important requirements to consider for spacecraft in general, and especially for intelligence missions and science missions. But since there's gravity, we can't really fully do systems level testing on ADCS systems. So I was wondering how you usually go about verifying ADCS requirements, or at the systems level. I would think this would be like a mixture of testing and then simulation, but
Yeah,
I
with
don't really know specifically
simulation
how
and
that.
analysis.
Yeah.
Testing, it's, you know, I mean, you can show where you're pointing, you know, where you can send a command and the system will actually point, but it really doesn't show you any ringing of the spacecraft or anything
Hmm.
like that. And so analysis, you know, good analysis will show that. And so it's mostly through analysis that you verify what your pointing accuracies. And of course, the pointing accuracy itself, you know, is distributed throughout the system. And so you've got to show, you know, where, you know, your ACS, for example, is contributing or not contributing, and everything else. You know, your stabilization, the sensor itself, anything that's been allocated, you know, to pointing accuracy has to be, you know, analyzed and demonstrated that it meets the constraints that have been put on it.
It's like when you got to the systems level, like even with analysis, did you ever have to do like any additional gain tuning once everything was in there, or was it's pretty much all just analysis
It
and until you get to orbit?
you did have to do some gain tuning, and especially with one of the big problems is that you, with certain systems, you want to be able to go from one target to another very quickly. And of course, when you stop the spacecraft, it wants to, there's jitter.
Hmm.
And you want that jitter to ring out as fast as possible. And so there took a lot of tweaking to that sometimes. And just anything that's added to the spacecraft can contribute to that. And that's, you know, that's where, you know, all of the original analysis comes into play. But sometimes when you finally get it all together and do system test and analysis of pointing accuracy, you're going to have to do a little bit of playing around and fixing some things, maybe stiffening up a little bit. Hopefully it doesn't take that. You can do it with software, but you know, you know, the number one goal of a sensor like that is that you have to have the pointing accuracy that's required. And sometimes it's really tough to get that.
Gotcha. So are you basically like testing the spacecraft in real time and then adjusting the gain based on a test signals of different types of like?
Yeah, when it's on orbit is the only time that you can really test it.
Right.
And what you can tweak depending on the satellite, whether you're using torquers or CMGs or, you know, whatever you're using, what you do is you tweak those.
Okay. So there are on orbit updates that are essentially done to fix that.
You can tweak it.
That makes sense. All right. And then you guys have prop systems too. So I mean, similarly with those, like you can't test maneuvers, but there has to be some way to verify that those are still at least operating normally, like during TVAC and vibe. So
right.
Like, did you normally just check for like leaks in the prop tank, or
yes.
were you mostly just looking at like nominal telemetry voltages, temperatures?
All the above. You know, you do leak checks and then do telemetry checks. And that was basically it in terms of ground test. And of course, you know, God forbid you get a leak, you know, once you've launched. And I've never seen that, but boy, that'd sure take your satellite out of commission. You know, if you had a gas leak out of one of your prop tanks,
yeah,
that would be bad. But you know, most of it was all done, you know, on the ground, you know, a series of leak checks and then, you know, telemetry for the rest of it.
Okay. What kind of telemetry were you looking at? Was it just voltages and temperatures, or were there other?
Mostly voltages and temperatures, and the prop components themselves were tested at the factory to make sure that they were working and putting out the right amount of energy, and that was really the last time it was done. And then the rest of it was, like you said, was, you know, telemetry and voltage checks just to make sure that you could turn it on and off, and that the software, if it was turning it on for, you know, a microsecond, that it was a microsecond that it was on and then off.
Okay.
So that was the biggest thing there.
Okay, so next question. One thing that I'm really curious about for large and more complex systems is how you actually like build everything up to a working system. So like more so in terms of, I guess, like software deliverables. So like on Phoenix, in order to get Phoenix to a fully working system, what we did is we would set milestone dates for certain demos. So like our first demo was, okay, just take a picture and then downlink it to the ground station. And so that kind of helped provide focus for, you know, all of these other tasks that we had to develop for the flight software, but it at least focused in on, okay, by, you know, this near term date, this is what we need to have done in order to progress and eventually get to like the full working system that we need. So did you guys do something similar, or was it mostly just software had all of the requirements, they just went down, tested it all out, and then once like they said they met all the requirements for a specific payload, then that was kind of delivered and you made updates from there?
It was really the latter. Okay. Of course, you know, we had fairly detailed simulators that they could test the software on. And like I said, it was tested many times. And of course, the configuration control on software is incredible. You know, every little thing is documented. And so they, you know, the software build was made. It was tested against the simulator. Everything was fixed, and then it was taken and incorporated into system test as much as possible. And again, anytime you were dealing with the real satellite, it was command by command. to make sure that it was reacting exactly the same way as it did on the simulator. Sometimes the simulator was wrong, and we'd run into problems and find out that a particular command did something that we weren't expecting. But again, running command by command, you didn't ruin anything.
Right. Though I mean, I guess now that I think about it too, you guys probably had a much more controlled process for how everything actually got on to the system. So I mean, like you have to have software reviews and say, this is approved, and now that we've passed this review, we can actually move into design, or like into systems integration, and putting all of these components together and testing them. Whereas like our project was a lot more flexible in that we didn't have that, and so we kind of just had to. We were just really trying to make it work kind of like as we went, and that was how we really learned everything. We learned all of the things that like we were missing or that we had to add at the systems level, and then incorporated it.
Yeah, software was really a system unto itself, if you will, and went through its own design reviews, and up to CDR, and it by the time that the command set made it through CDR, it was pretty much perfect. Very few problems with command software. Again, if the process was followed and everybody did their job, there were very few problems because they had the simulator to find problems. And they had a lot of them before it hit the floor during system test. But usually by the time it got to system tests, they were pretty good.
So speaking of like systems level testing, that's definitely like one of the most critical phases of the entire project.
Yes.
So what drives like the level of testing that you do at the systems level, and how like meticulous that it really gets? Is it just mostly just funding and like budget and schedule, like we were talking about earlier? Or?
Well, I think system test is one of those things one of those items that is driven from the very beginning and designed from the very beginning, because if you do your requirements right up front, you're doing a requirements verification and test matrix, and showing at the system level, and it's also done at the subsystem level, but we're talking system here. You're showing at the system level how every single requirement is going to be tested, how it's going to be tested, and what the result of that test is. And so that defines in toto what your system test is going to be, and you can also from that define what your cost is going to be.
Okay.
So it's from that RVTM that it's kind of like a requirements WBS, if you will. It defines your system test and how extensive it's going to be, and how expensive it's going to be. And the customer can always say that, rather than by analysis, the only thing we want to make sure of is that it's getting 12 volts. So just show us 12 volts rather than going through this detailed analysis to prove something else. They can always say that. I've seen it happen in a couple instances, but not many, because usually the engineers that are putting together the system test engineers know what they're doing and why they're testing and what needs to be the result of the test in order to ensure that you have a good product. And so it's really that requirements verification test matrix that defines system test and how extensive it's going to be, the schedule that you can run it on, and the cost of it.
Okay. Yeah, for us, that was definitely, I think that the level of systems testing that we got to at the end for us was mostly driven by schedule when it came down to it. And, and we did as much systems level testing as we could along the way. So we would work towards like these minimum goals and objectives, and then work on making it better from there. And eventually the the system became a much more robust system. But yeah, it was definitely, we were definitely limited in what we could do based on how close we were to delivery. Like we weren't able to get in a lot more of our like critical power testing at more of the systems level, because so much of it was just taken up by software development, making sure that all of the key components of software were there.
I think, you know, probably from listening to you, you know, one of the big differences between the, you know, the CubeSat that you've been working on and some of the, you know, the really large systems that go up is that they are much more structured processes and have a lot less room for a little schedule slippage.
Yeah.
And you don't have to be quite so structured, you know, with the CubeSat, which is good, I think, because it gives you a lot more leeway, you know, to learn.
Yeah, and that was, I mean, that's definitely like another area where there's a very large disparity between larger and more complex spacecraft versus CubeSats at the university level, is that we didn't have a lot of that structure because there's so much that we didn't know. And even, I mean, Phoenix took 3 years for development, and even then there was, you know, we were still always, you have to learn all of the subsystems and what goes into that, and then also how to be efficient in putting all of that together. And so, yeah, there was a lot of stuff that we definitely didn't really start to get right until the end. And we finally got like a pretty solid process down. It's interesting to talk about the differences between like your experiences versus mine because of that. So,
but when you come right down to it, it's not that much different. There's some subtleties in the scaling, but it's not that much different.
Yeah, I think it's interesting to talk about the differences between like your experiences versus mine because of that. So the same team were to develop, you know, a different CubeSat now, like it would probably be structured, maybe not to like the same level, but it would definitely be a lot more structured than it was, you know, since we had to figure things out along the way, essentially. So kind of ending more of the testing and integration questions, I have to ask, what are some of the most craziest and or most terrifying schedule issues that you've had to deal with, aside from the payload, the sensor example that you gave earlier?
Other than that one, I don't think I've ever had one. We've had to do schedule changes and do rolling waves. Those aren't scary, they're very stressful. When you know you can't make schedule, when you know, for some reason or another you have a slippage and you have to start doing rolling wave schedule changes, where you're just doing a few weeks at a time.
Oh, gotcha. Okay.
And hoping that you can somehow or another get back on schedule. You may have moved your schedule out, but what you do is you plan for whatever the customer wants. It depends on how drastic it is, but you know, here's what we're going to do for the next 3 weeks, and then here's what we're going to do for the 3 weeks after that. And hopefully what happens is, after a lot of wailing and gnashing of teeth, the program gets back to where you can, between yourself and the customer, approve a new schedule and then stick to it.
Okay.
And in that, unfortunately, happens way too much. You know, you're always optimistic, you know, when you sign the contract, and you know, over even a couple of years, things change and you run into problems that were totally unforeseen. And, you know, hopefully what you can do is prepare the customer for it. You know, the worst thing you can do is go and tell the customer that 3 weeks ago we knew that something was going to happen and we never told you because we thought you could fix it. And that never goes over well at all. But I think that's the biggest thing, is that you just have these unforeseen circumstances and nothing can be done about it, and you just have to keep the customer apprised of it.
Right.
And, cost and schedule are always issues. Technology is, only once did we run into a technology issue that we didn't think we could meet the performance requirements, and it turned out we could and did. But it's cost and schedule that drives you nuts. In both of those, it has to do with things that change that you don't have any control over or didn't think you had any control over.
Yeah, I mean, I think all of we definitely did that several times when developing Phoenix. And we look back at our old schedule and just kind of laugh at ourselves and be like, oh, we were such fools to think that was possibly even achievable. So I mean, pretty much a lot of our schedules towards the end were definitely like rolling waves, because like I said, we were learning throughout the whole thing, and so
Yeah.
there was just, we would shoot for a large date for a large milestone, and then try to meet that as best as possible with developing smaller, more achievable milestones about 2 weeks out that we could actually complete. And throughout the design phase, it was definitely a lot easier for us to meet like our PDR and CDR dates and have a lot to really demonstrate. But when it really came down to developing the software and actually working with the hardware, that definitely became a lot more difficult to manage. And we did a lot of that. So one more question on schedule. What were just some of the biggest lessons learned that you learned in creating schedules throughout systems integration and test?
Well, I think the biggest thing was that, Murphy's Law is always in effect.
Mm-hmm.
You've got to keep a positive attitude, but it just seems that Murphy's Law bites you every time. If something can go wrong, it's going to go wrong, and you just try and prevent, do whatever you can to, keep everything on track. But that's the biggest thing with schedules, is that one little slip one day can cause a huge slip a month from now. And so you just try and keep the schedule as best as you can. But it's really hard to do, because there's so many unknowns out there,
Mm-hmm.
when you're dealing with these systems, and that's what bites you, and you try to have people that are constantly looking for that, what can happen, and what's the probability of it. And that's all part, I think, of a good upfront risk analysis too, not only with the technical part of the system, but also cost and schedule. What is your risk with cost and schedule? And if people are honest up front, in the beginning of the program, maybe you can prepare for things to come. I think I just happened to think of one of the issues that I had to deal with is a machinist strike at Lockheed. And it was well known months in advance that there was a high probability of machinists going on strike, and nobody took it into account in a program, in any of the programs. And when they went on strike, it was mayhem. And schedules slipped, costs increased, and a lot of that could have been alleviated. It couldn't have been done away with, but alleviated. The cost could have been cut down, and the schedule slippage could have been cut down if it would have been taken into account up front.
Mm-hmm.
And it wasn't. So that was a kind of a known unknown if people would have thought about it.
Mm-hmm.
But it's, those have to be taken into account, and then it's the unknown unknowns that really bite you. If that just came up all of a sudden and it was a wildcat strike, then nobody knew about it, nobody could do anything about it, and you just have to take it, and the customer has to understand that too. They may
Mm-hmm.
not be happy, but there's nothing anybody can do.
Yeah, definitely. All right. Well, I have one more question. last one, and this has been a really like awesome conversation. I don't want to keep you for too much longer. So final question is, do you have any like noteworthy systems INT memories that you would like to share that you haven't already? Can be a horror story, and a tale of woe, or a tale of triumph.
I think I've shared everything. There's there's one corollary to Murphy's Law, and that's they call it Finagle's Law, and that's that if anything bad is going to happen, according to Murphy's Law, it will happen at the worst possible time. And that's Finagle's Law, and it somehow or another, both of those, we laugh at them, but they're true. There's most of, if something goes bad on a satellite program, it's never a good time. And it's most of the time, it's the worst possible time that it could happen.
Yeah, but, we experienced like three completely different cases of those on Phoenix within just the final month before delivery. So that was fun times. Said with much sarcasm.
Understood.
Yeah, I would do flight integration again. Like it was awesome and rewarding, and I loved it. But I also don't want to do it again. If you know what I mean. So.
Go into systems engineering.
Mm-hmm. All right. Well, that's all I have.
Okay.
Thank you.
Well, it's been fun.
No, this has been awesome. Thank you so much for doing this again with me. I really appreciate it.
Hope it was worth your while.
Oh, absolutely. Thank you all again for tuning in to another episode of The Art of Space Engineering. I hope you found this conversation as fun and informative as I did while recording it. So tune in every 2 weeks for more adventures on space engineering, and if you like this podcast, don't forget to rate the series, share it with your friends, and follow us on Facebook for future updates. Here's looking forward to future adventures and the lessons learned from them. Cheers, Sarah.